Welcome to the second week of the Atrial Seminar, and this week we have a guest that was a student here. Now he's a professor, Francisco Junior Evangelista. He's currently at Cal State Los Angeles. He finished in December with his PhD here in concrete pavement and analysis. And he's already taught several classes at Cal State in different subjects, including pavements and mechanics and numerical methods. Is that correct? And he'll be talking about a little bit about some of the work he did on his thesis and some further validation of that work that since then today. So please welcome Junior back to the university.
So thank you very much, Jeff. Thank you very much for your presence here. It's very good to be back here in Illinois. Not so long time ago I was here, exactly sitting as you guys are now. Think about the future and how are you going to do. So for the topics here, as Professor Raisler mentioned there, I will talk about some of the results that I did in my thesis and some updates and some further validation that you did, also with some results from here, Illinois. That's why you recognize all the symbols that I put it here as acknowledgement that was basically done with the SEAT support and the ACRP, the Airport Cooperative Research Program. And I also did the working collaboration as Professor Raisler, as my advisor, and Professor Armando Duarte, also from Illinois, right, the civil engineering department in structures. And we are going to talk about here two-dimensional modeling of failure in quasi-brittle materials and structures, especially an approach that you have been. What is it? Yeah, it's giving like a interference. Yeah, it was in my pocket there. Okay, so that was basically what I'm going to present here, especially a nonlinear strength approach for concrete slabs. You are going to use the validation that is slabs, but this can be applied for any concrete structure and in different shapes, geometries, and size, as I'm going to explain further here. So as introduction and motivation, as you can see here, concrete fracture and failure is very challenging, especially because it's a quasi-brittle type of failure. So it's a failure that's not linear elastic, you have today analytical solutions for it. So it's a more involved thing because involved, like, as I put it here, a fracture process zone. As you can see here, if you have an open crack, as I put it here in this black part here, that's any concrete structure. This is applied to any type of, let me come back here, any type of concrete. So you have the crack, and ahead of this crack you have what you call FPZ, that's the fracture process zone. And most of the time this involves like nonlinearities and some more complicated behavior in terms of prediction of this failure. And another thing, you see that concrete is present in a couple different structures here that I can put it, especially what you're going to approach here is for airfields type of structures. And another thing that's challenging is that you have the size effect. So you characterize your material in the labs, and I put 3 examples here of some characterization for concrete that you have been developed here, some classical ones, and the GCT for concrete that's also used in asphalt. And you have, this is the small scale type of characterization. But what you wanted to predict is exactly the real scale here, as you can see in different types of structure. That's also challenging how to do this type of transition and how to predict well. The other thing for the motivation is that if you consider like fatigue, this presentation is not going to be about fatigue. I'm just showing like some fatigue curves here, is that if you consider like here in the y-axis here, you have the stress induced in the structural member over the concrete strength. In this case of this top graph here is the measuring on a beam, is the MOR beam, or the 4-point bending. That's a classical test for concrete. That's a strength measure there. So, and this is the number of repetitions, the number of cycles to failure here. That's what we call SN curves. So if you see here, if you divided the induced stress in the member, structural member, in this case, for this curve here, you have the slab over the MOR, the strength of the beam, you get this curve. But if you use the stress induced in the beam over the MOR of the beam, you have this curve here. And you see that because one is slab and one is beam, you see that you have different types of fatigue curves here. So it's depending on the shape, at least. It's the first conclusion that you can tell from here. One is slab, one is beam. But in the same time, if you just change the numerator here, and instead of use the MOR for the beam, for the slab, the induced stress on the slab, but you still use the MOR for the beam, that's the correct, right? You use like the strength that you measure in the beam over the fatigue test for the beam, but now you use the strength from the slab now in the fatigue of the slab, and you see that you match the curves. So what doesn't mean is that what really you don't know and what you really want to predict and use it to predict here is exactly the key aspect here is the strength of the slab. So the strength of the slab that is going to characterize. Now you have both materials here, both structures, more or less the matched curve. That's exactly what you want, like a material property that's independent of the geometry of the specimen here, of the specimen of the test. So what do you want to do here? You want to try to understand the failure of concrete, as I said, this quasi-brittle type of behavior. That's something in between the linear elastic and the plastic type of behavior too, type of failure. And you have what? You have the three bottom lines here, the lab scale here with the material characterization, or through beams or other different geometries as the DCT here, the disc compact tension. You want to incorporate the computational modeling with accurate predictions for the model here, and exactly to also predict the structural scale here with realistic boundary conditions. As an example, a real aircraft in a air-filled concrete slab. So that's what our main objectives here. More specifically, you wanted to formulate an efficient nonlinear fracture mechanics approach that can account for this fracture process zone and all the nonlinearities that the material shows prior to failure, that induce the failure, that you call here a nonlinear strength fracture modeling, or LEFM. Also extend the nonlinear elastic fracture mechanics approach, as I'm going to touch a little bit about this in the future here in this presentation, equivalent elastic fracture approach. That's also well known. That's for example, the Bazin size effect model to 3D structures, because if you go in the literature, Bazin has like a couple decades in working on that, and all the works are in 2D type of predictions. And you want a more realistic type of structures, as I showed, the 3D slabs, and that's what we want to extend to this kind of prediction, more realistic. And also quantify the ultimate strength. So what will be exactly the peak load or the strength of these slabs? Because as I show in the fatigue, you have two ways to do it. Or you really cast a big slab, a real size slabs, and test it, or you can develop models that's exactly the three interactions with lab characterization, computational model to predict this. And this is much more cheaper in terms of all costs that you have, right? Like money-wise, time-wise, you can do that. You don't need to really cast a real size slabs. So in terms of the procedures of the analysis that you did here, so what do you have? You are in this small scale material characterization here in the yellow. And you want to arrive in the real scale structural strength with realistic boundary conditions, in case 3D, air-filled type of slab here. And in this path, to arrive here, you have the size effect model, because you have a size effect. You're having two different scales here. And in this specific field here, you have designed a high order approximation for the size effect that try to predict the ultimate strength of the real scale here that you are interested in. And as a specific, using this kind of already known knowledge in the literature, you develop a methodology that is going to use linear elastic fracture mechanics simulations. That is easy to do. You don't need any nonlinear type of model to that. for 3D domains, and also use a flexibility of a numerical method, that's the GFEM, that you can put different cracks in the domain without trying to fit the finite element mesh with the crack that you want to simulate. I'm going to show more details in a couple next slides. And also, you are interested in the fracture mechanics characterization with size and shape independent properties. So these two feeds here, one part is lab, one part computational here, and you develop like a semi-analytical model, and you can approach this real scale based in the small scale characterization. I'm not going to enter too much in details of this, but this is most of the formulation that you did here. So if you have a solid here that you have a crack, and you have applied stress surrounding this existing crack that you have, you do energetic approach and formulation here, and you can calculate that the maximum stress that you can induce in the material according to the linear elastic fracture mechanics. Let's concentrate in this one here, is depending on what a K that you call stress intensity factor, that's going to tell us how much the stress is amplified because the presence of the crack. And you see in this, C value means that this kind of amplification has also a material property. So instead of in the strength theory, you have that the tensile strength will be your criteria, or if the stress in a given structural member is going to exceed the tensile strength, this is going to fail. But when you have the presence of a crack, all the mechanics change. So now what you have is that if the stress intensity factor developed in the material is greater or not than a critical value, that's why you have C here, you are going to have the propagation. And all the other ones you see here, you see like these are geometric factors here. You don't have any other material properties. So linear elastic fracture mechanics, the maximum stress that you can apply to propagate this crack is depending on these material properties here and some geometrical effects here. A is the size, the A is 0 here, and F is a geometric function in function of the geometry and the loads that you have. In our approach, it's slightly different because it's considered the linear elastic material. In our approach, you consider some region ahead of the crack tip, as I showed the fracture process zone, as one of the main mechanisms that this failure is gonna develop. So we base it our formulation, and you do just a asymptotic expansion this over this crack, and you realize that you account for some size of this fracture process zone that I call C here, and you do like a Taylor series expansion, already consider this size for the structure that you want, and you arrive in a different equation. Consider this G already with the C value. So what is C? Is the A0 that you already have plus the size of the fracture process zone. So that you plug it here, you also have equivalent stress relation that also relates to material properties here as model of elasticity and the energy, that both here has an immediate relation with the K, and also these geometric factors that you do here. That's more or less what you did here. So we arrive with the following situation here. You want the structural strength of evolving crack size. Consider like a simple supported slab here. So you have a crack size A0, 1 here. This is a little one that's already this crack propagate a little bit here more, and another one that's keeping propagate towards the top, for example, in this case. And you have a typical load here over the thickness here. So what are they going to exactly try to predict this? What's the ultimate stress around this crack tip here that's going to evolve this crack to totally failure this type of slab, for example. In this case, a simple supported one. So our general approximation is given by this expression here. It's just this equation. So this is the strength, and you have some terms that incorporates material properties, that the yellow terms here, for example, that's just the numerator that you can see here, and some other ones in red, that's the structural geometry and load dependence, as I put it here, as this G function. And if you expand these terms kappa and beta here, you have the other material one, that's the size of the fracture process zone, that's proved to be a size independent property of the material, is also a material property, over the d, the thickness that the crack will propagate it towards it. So that's what you have here in the psi equation here. And the expansion of this beta here, that's just geometrical factors that you are going to take into account. And just a detail here is that this is a summation here because it's an expansion. So you can have like let's say, theoretically arbitrary number of terms here. So that's why you have ON, that's the order that you apply. So what order to use it here? That's why sometimes I use high order, when you use more terms in this expansion. So you have here, because this is a summation, I'm just repeating the terms here and define this G function here, what it is here. And you have a high order one. Why? For example, this one you have three terms. Three terms, one is the zero order, first and second one, for example. And here I plotted the contributions of each order. Here you have the contribution of this, for example, the kappa 0, beta 0 here over the entire term. As you have here for this line, over the size of the fracture size. The notch that you have as develop here over the the thickness of the slab, for example, you have 0, you have no notch, right? Until 1, you have the entire crack passing the slab. And you see here in the beginning, when the crack is very small, the first term doesn't have too much contribution, but increase very quickly here to a lot of this contribution, the normalized contribution. The other terms, you can see here that it starts with greater value, for example, the second order term, and try to decrease when you increase the crack size. And you see here, this is a 0 value, more or less right here when I'm indicating. So the third order start with some value here and very soon decrease for 0 here in the contributions. And of course, this depends on the material properties that you have. So that's why you just adequately use a second order approximation for this case here. You don't need to put in more terms. But sometimes if you have these third and fourth terms that has some contribution, you also can incorporate and you can also, you are going to be improving your response. But in this case, it's not necessary, as you can see here. This term here is already gives just some contribution in very small crack size and already goes to 0 in terms of contribution. So for this part here, you also use like a novel technique that has been novel in terms of the comparing to the existing ones, as it's already like 6 decades. That's the finite element method. You have the generalized finite element method here. That was, as I tell you, it's a novel because in the last 2 decades, 1.5 decade, since the middle 90s, I guess, yeah, that was developed here. And it's going to help us a lot because, again, I'm not going to enter in details of the method here, but you use in the finite element course, I don't know how many of you guys have some class in the finite elements, but it's a numerical method that tries to solve a problem that you don't have the means to do with the analytical solution. So, and you approximate this with polynomials, generally like low order polynomials, like linear polynomials here. That's what's this first function here. And that's you have your approximation. So to approximate something that's, let's say, is a cubic function, and you use linear polynomials, is intuitive things that, oh, yeah, I can decrease the size and have a lot of linear terms, right? And I can get the answer. And in this case, but what about if I have a way that I can combine already some knowledge that I have for this function, like a type of enrichment function, AL, let's say a second order polynomial, and I can do the product of a linear one with another linear one, and I have a quadratic term. And I already can, with the same framework, already approximate it with the same number, with a limited number of the elements that I have. This is more important if you have a crack, for example, because in the crack here, if you see, this is 4 elements and you have a crack passing through the elements. So what a crack does in the solid, creates a discontinuity. So with the discontinuity, you can apply, instead of a polynomial, but a discontinuous function here, as I call this HL function here, When you multiply the product given by this is just the expansion of the entire term, you have the combination of these two functions, the standard finite element shape functions with a discontinuous one, and you can still get a combination. It's like the best of the two worlds here. So what you have here, I can simulate something that's discontinuous, has a jump in terms of the response, with doing too much elements to simulate like explicitly this jump. That's what's the main advantage. In practical terms, what does it mean? I can insert, like, for example, a crack in my model, and this crack can pass through the finite elements. And I just apply these functions here, and I can catch the jump of this crack passing through it. That's what's the main advantage. This is just some details of the functions that I use. And this is part of the code. Why I use it here is that that's in collaboration, as I said before, with Professor Carlos Armando Duarte from Civil Engineer 2. He has a tool that's under development here in the university that handle arbitrarily crack growth in 3D domains. As you see here, you can put this is a crack surface that indicates 3D, right? So you have the crack surface. And this geometrical tool can exactly map where this crack is passing through the elements and apply that special functions to it and try to exactly model this jump in between that the crack is going to induce in between these elements, inside the elements. So that's the computational tool that we have. The other one is the equivalent less crack models tests. So based on this, I did not enter too much in details, but you have a couple ones that's in the literature here, but you choose a specifically one that's the jink shot that's already a standard. Now Riley standard here. And you have the characterization of the fracture property of the concrete by the critical stress intensity factor and the critical crack tip opening displacement. So with these two parameters here, that's why it's called two-parameter fracture model, you can, another way, I can put it in my equations and adapt these two properties here, and I can estimate the G. The G here, is the fracture energy, the initial fracture energy. That's also a material property that has a direct relation with I did not put the equation with the critical stress intensity factor. And the CTOD with K, along K, also relates to the C. That's my size of my fracture process zone. And because the two-parameter fracture model is specimen independent and size independent, so you can do in any specimen that you want. Maybe it's a little bit dangerous to say it now, right? If compare, you can do in beans or in DCTs. They have to yield the same fracture property here because it's shape independent. That's why you choose them. And I can feed my model with these two properties here. So that's what you did for my validation here. This was performed by Armin, I guess, right? This was part of what he was doing when I was more or less about to leave. He was conducted exactly the discompacted tension for the concrete here. And this was in the slabs that's a previous project here that Victor did with some slabs that are outside there. So they core some DCT specimens out of the slabs, and you have here the fracture properties, and also test the slab. So I can use exactly these two things to validate my model. Since I have a small scale test that was cored out of the slabs there, outside here, atrium, and also they test the slabs. So that's what I did, but this is the results for just the lab. And here you have the two-parameter model that's a couple loads and unloads there to calculate the compliance and get the properties there. So let's go to our three-dimensional validation there. So as I said, the slabs were outside, some slabs were cored to get the DCT ones, and you have the big slab that was tested in the other facility, in the other building here outside, still in atrium. And you have this dimension of the slab, 1.8. It's not a real size slab, but it's still large slab compared to the specimen, right? It's a large structure here, 1.8 by 1.8 meters here, 15 centimeter thickness. And the MOR was 7.5, and you have the load plate that you have 20 by 20 centimeters. So you apply the load here in the slab and test it. I'm pretty sure that most of you, if not all of you knows what I'm talking about here, right, in the other building there. And so you have the soil foundation here, you have the slab. As I tell you, you test the slab here to see it, and you get already previous results from the DCT, from the properties. So let's see if my model works, if I can exactly predict what will be the strength that this lab is gonna have, just based in the lab properties. For this came my modeling part. That's the 3D model. This you can see. And to work in my expansion, I have to calculate the geometric functions. The geometric functions just relates different crack sizes to the geometry of the model. So I have to simulate different crack sizes here. In this case, I choose through the length, rectangular through the length crack, as you can see here, that I put in the model. This is a zoom up in what I'm talking about as the load. And I can calculate some geometric functions that's going to enter in my model there, in that expansion that I developed there. So with this, I have to do some simulations there, and after that, I plug in my equations along with the material properties. Example here is that this is the slab, the deformed shape here, as you can see, as I simulated with different crack sizes. Look at the crack here, that's through the length. And this I have the crack. And this 3D graph here, it's exactly this geometrical dependence as I'm talking about. The K here is the stress intensity factor, how much the stress is amplified with the presence of the crack. That's my Z direction here. My alpha sub 0 here is the different cracks sizes that I simulated. You see from 0 means no crack. That I don't have, I start with 0.05% over, because this is over the depth, until 0.5, until half of the depth of the slab with the crack. And this is the position in the crack front, because remember, this will be the crack front in the slab. So we have the point A here, that's close to the edge, that's at the edge here, and this means exactly this variable here. So, as expected, just for us to place in this graph here, for example, if I am here, I'm exactly on the edge, because this point A here is exactly here on the edge, right? That's right below the load. So I have amplification of stress much higher than when I'm going point B here, that's away, that's this from the load. So you have the decreasing here. That's what I have. And also this increase, as you can see here, is 3D, but from in this axis, increase the size of the crack. This is a crack of 0.5, half of the depth, until one that's 0.05, that's like 5% of the depth. So exactly these geometric factors here, that is just a line over the surface for this case, for this point A, that I will plug in my equations there for the asymptotic expansion. So let's go to some results here. So what I get here? First I have the experimental ones. This red one here is 3 red. All the reds here is experimental, as you can see here. This one, this other one, and this third one here. I also perform a cohesive zone simulation. That's right now one of the most used ways to also simulate the crack propagation. It's a nonlinear model that has been used like in the last 3 decades, and a lot, like most of the people that I can tell you that work with crack today, maybe 85% works with cohesive zone models. And it's a nonlinear model. You have a lot of problems. One of the reasons that you are not I personally try to discontinue use that is because it gives a lot of trouble there in terms of convergence, because it's a nonlinear model. In terms of mesh, that you have to do it because you have to put the mesh in most of the implementations. You have to put the crack already, the path that the mesh is gonna propagate. But for this case, I did it here, and this is the red, the green line here. And you see that, look at the 3 peaks. I have this is experimental, this experimental, this experimental, and this is my cohesive. That's pretty good, I guess. Right? If you take the average between these 3, you'll be something like here, and the cohesive is not that bad. And this is the load capacity, like the load measured here until the failure of the slab, right? That's the maximum in the peak. And if you use the strength theory, that's exactly the stress, only the stress in the bottom here with the MOR, you have This line here. That's, as you see, how your strength was predicting much less than what was developed in the slab here, in terms of that was this line. Okay? That's what you did with this tool. Now I'm going to apply my model. I'm going to show comparatively here. And just a detail, this was tested with no notch here. So it was a plain slab, a notched slab. So when I go to my model here, what my model is going to present to you, I've already told you a second order approximation. I plug all the terms here, and I get this. This alpha means size of the crack over the depth of the slab. And you see here that you have this curve here, the black one. The blue shade here is just the standard deviation of the fracture properties. And here you have the strength, right? That's load over the air, load over actually the strength here is defined as the flexural stress in the bottom where the crack will develop, the crack that failures there. And here you have the MOR, you have the 7.5 MPa, and that's what my model can predict, exactly the develop of this curve. Now what does it mean? Doesn't mean that if you give me your slab 3D, a 3D slab, that slab, and you tell me, oh, this slab has a notch or has a crack that extends all through the length of 0.2, like the ratio between the crack size and the depth. And I go here and I can tell you what will the load would be. This case, 44 MPa there. Load not, this is stress that is induced by the load. You have the direct relation. And I told you that slabs were tested what? Unnotched, right? So what's the alpha that I have to look at here? The 0 one, right? 0 means no crack. That's exactly these points that I have here. Just to a better visualization, just a zoom over that part of the graph until alpha 0, until 0.1, so 10% of the depth. And you see here, how predict this black line here with touch 0 is my prediction. Shaded region here is with some standard deviation here, plus or less 1 standard deviation of the fracture properties. Look at the green one, my cohesive simulation was right here. And the experiment, that's the test of the slab, that's in this paper here in 2012, was the 3 red ones, right? You remember the red curves? And look at how my predictor were almost in the point there. And of course, I have still a range here that's more 1 plus or minus 1 standard deviation for the 0 one. And also the cohesive was pretty good because this variation is it's like 10% variation. So you have, the cohesive was still predicted over the standard deviation of the fracture properties. And my model could also predict this. And what happened if you use the MOR, right? With no fracture as you do today, you use the MOR test, was 7.5. Look at what it is. So out of range of the capacity there. So when you go to that fatigue curve, if you divide the stress inducing the slab by this, that's why you have the shift of the curve there. Now you have to use actually these values here. That's exactly the values predicted in the slab. And this was predicted by the model, and I used the test exactly just to compare with. And go here to compare my model, that's LEFM, the proposed one, right? The linear elastic fracture mechanics that doesn't consider this fracture process zone ahead of the crack, and some strength predictions. So the strength you already know, 7.5 here. This also, in the x direction here, you have the alpha, that's crack size over depth, and here you have the predictions here. So that's the same curve here. That's the proposed model one, the solid one, for different types of crack size, for different crack sizes there. Look at the predictions of the linear elastic. If I don't consider the nonlinearity of the material to this prediction here, you have this dashed line here. Look at that. The dashed line is pretty close to the solid one that considered the nonlinearity until some point. When you get very small cracks, you see how they start to diverge, and they go until infinity. This is going to be asymptotic behavior here. So I cannot predict for very small cracks, especially the ones that tend to 0, so unnotched slabs, with the linear elastic fracture mechanics. But I could predict with my model. That's the same things there. The red, the same graph that I showed you there. And the red line is related to this axis here. It's just the ratio between linear elastic and nonlinear elastic. And you see that the ratio tries to go to 1 for some small cracks. Why does this happen there? Why, when you have alpha goes to 0, you diverge in between the linear elastic and the nonlinear elastic? As you see here, is because the size, just remember, this psi here is the size of the fracture process zone over D, and alpha is the size of the crack over D. That D is the depth of the slab. So it means that when you have a crack size that's much, much bigger than the size of the fracture process zone, that's exactly the zone ahead of this crack that is going to induce some nonlinearity, this nonlinearity, the C, doesn't make too much effect because the A is is bigger than the size of this fracture process zone. That's why you have the convergence of the terms. But when this alpha, that's the size of the crack, decrease, so what do you have? You have that if decrease like for, let's say, 5% of the depth, and let's say that C over D, that's this psi, this is fixed because it's a material property. So if it's like 0.01, 10%, you still have a difference of 10 times, right? So the crack size is almost the same size of the fracture process zone. So the zone that the nonlinearity happens is almost the size of the crack. So that makes a lot of effect. But when the crack is too big, that the size of the process zone that doesn't change, is a material property, is smaller, it doesn't matter. That's why you can use the linear elastic fracture mechanics here. That's why the ratio goes to 1. And here, just to show advantage here, comparing with the cohesive, I told you that the cohesive is a nonlinear model. So you have iterations to arrive in each step of the loading until you arrive at the peak. So what you have here in red, I use, I think that 56 time steps to arrive in the peak load. So for the same mesh and finite element simulation, for me to predict this peak load, I have to pass from 56 steps. That's why I multiply this for 56, the number of equations that I'm solving this numerical problem that's related to the finite element mesh. But for my model, I just need to do a couple different crack sizes there, and I get the function, and I do this as a post-processing, and I just use 6. That's why I just have this. And here you have the number of equations that you have to solve in the numerical process to predict it. For example, the cohesive here is 2 to the power of 7, right? Equations here. While the ones for my model here is 2 to the power of 6. It's 1 order of magnitude in terms of equations that you solve. An equation that you solve translates in time, right? Because you are using like a computer to solve these equations. A linear solver to do that because you have to solve all these equations to get your answers there. Another thing that you can do this that is very interesting is, how long time more I have? Like 5 minutes, right? I just want to pass this is, since I can plug some fracture properties in my expansion, my equation, the developed equation of the model, I can already do graphs that I have all the material properties that I want and plot this curve for different crack sizes, as you see alpha 0 here again, and I can get the strength of the slab. So now you can give me, since I'm doing this in my equation, you can give any material properties that you want. So you characterize in the lab, and I can already have the curve in terms of the curve of the strength for the geometry that you are interested in. That's what most of this graph does. And this is the variation for, instead of fracture energy, is the variation for the size of the fracture process zone, my C here. See here you have a very nonlinear effect when the C is very small, as you can see here, and the alpha also tends to small. Okay? But what do you want with this and what are you doing right now? This is just the validation. I did not perform like an adequate validation in my thesis. I already assume that it was right, but don't do that, sometimes not. But here what I also develop in my thesis here, that's what you want. You want to really real situations, like this one. That was a FAA project that we were involved for years here. That's the A380 aircraft here, and you have the triple dual tandem here, loading some slabs in a given way. This is for the belly load, just for one gear over the slab. And you can do exactly the same that I did in a very more complicated situations, right? It's not the simple case that I validated that was tested here in Atru, but this is a real situation. I have a real slab with a real load of a tandem, and I just construct my surface of the variation of the stress intensity factor of different sizes of crack here. And from this, I derive my geometric functions, plugged with the material properties, and I can calculate the strength. And I can, for a given set of data that you gave me in terms of material properties, I can calculate what's the strength of this slab for different crack sizes. This can use to predict in terms of how the crack develop, but can use in the other way, like a non-destructive type of methodology. You can go to the field, measure a given crack size, and you refit the model here. You can estimate how much is going to be the strength of that slab with the given crack size. If you go there with any methodology that you want, and you give, well, in this slab I have a rectangular crack, more or less. In this case, it's through the length that I use it. That is measured the depth, the average depth, or some variation is, let's say, it's 10% of the depth. And I do my model here, plug it. You have you can core with the GCTs, but in this case it's destructive, right? But if you have the material properties that you have before the fracture one, you just plug it here, and I can tell you what's the load that crack will propagate with this existing crack that you have in the field. Can think in this way too. And this is another real situation, but it's the same thing. But now you have the belly load. You cannot see too much here because the shades, but you have the two gears over the slab here, through the slab, for top cracks, and you predict the same. So what are you talking here in terms of conclusion is that the structural strength is strongly dependent in the geometry, fracture properties, and initial crack size. It's an interaction of these three. It's not only material properties, so because you have the size and the shape effect. So that's why you have the difference between the fatigue curves. If you have a beam, it will be one thing. If you have a slab, it will be another thing just by the geometry itself. And also you have the fracture properties that you characterize on the lab. And the initial crack size, if that structure will have a crack, already existing crack there, all these interactions that give the strength. So of course, crack position and the assumptions that you have. And you see that the proposed model here try to quantify it. I even show the difference between the linear elastic and the nonlinear elastic there with the test that was performed here in Atru, the monotonical load there. And the proposed model was able to predict even is very small crack size, even the ones that tends to 0, so that will give the unnotched slabs, and I compare with the lab results. Of course, as everything has its limitations too, and the main limitations that I could put here is that's mode 1 propagation. So what is mode 1 in fracture mechanics is that the crack surface is going to open normal to the applied load, so you don't have shear type of failure, in plane shear or out plane shear, if you imagine there's like two crack surface. I just consider the mode 1. That's exactly the normal opening of this crack. But in that case of the loading that I show, it's a typical case of only mode 1, if you have that kind of situation. And of course, I consider just through the length cracks, because there was a rectangular crack through the length. But you can apply, and I already try to find time to develop here for quarter elliptical cracks and do the extension to partial cracks. And of course, as I told you, everything is an interaction between this small scale modeling and the real size structures that you may have. Try to predict this strength. and have a very good accuracy in your predictions and save time. So I think that's all I have to show today. Thank you very much for your attention. I'm welcoming you if you have some questions, comments, suggestions. Thank you.
The crack, okay, but in the transverse direction.
Let me just, so how I found K, right, the stress intensity factors,
K1.
along the slab length.
Yeah.
Let me,
If you go back to the picture where you have the slab and the crack. Okay, this one.
This one, right?
Yeah.
Okay.
You are plotting it along the crack and in the transverse direction, right?
No, just this direction here.
Show the next plot.
Because I have that in the next plot, yeah. Look, that's my slab, loading, and this is the crack. So I can calculate the stress intensity factors from here, this point, that's this one here, until this point, that's in the other one. Because in the numerical tool that I can use it, if I have how much the stress is going to be amplified, I can calculate in all the crack front, because this is the crack front in red here, this line in red. So it's the same. So it's through the slab length here.
In the x direction?
I think are you confused with the surface?
No, I'm asking about K1.
Yeah. But
Yeah,
on the
you mean
bottom
x direction, this direction here?
No, on the XYZ, in the 3D model,
Yeah, no, I'm
Yeah,
just
this
plotting the y direction because I don't have in the x direction. The x direction is just a line now. Look. Look, in the zoom here you can see the x direction, that is this direction, is just a point. Look, this is just a point. You just see like a point. You see a line. As you see a crack in a slab that if it was a straight one, you see just this point there. You don't have directions there for the crack, just the longitudinal direction as the crack goes through the slab. So there's no x calculations here.
I think the surface can be confusing because it gives the impression you have it.
This surface here?
No, the 3D surface plot.
Ah, okay. Because,
It looks like you have.
yeah. No, because one is the s variable here, that's the y direction, but the other one is the size of the crack. Okay? That's why it's a 3D, but this is not translating the space. This is the y direction, and this is this a variable here, the size of the depth of the crack. And this is the k. Okay? But the crack is just in one direction. Any other questions?
How about some comments on whether you use this for asphalt, since we have a bunch of asphalt people?
That's a tough one. It's the same comments that happens with the concrete because, but concrete it's less observed. But the question in asphalt is even the initial question. That's the fracture properties itself. So if a 2-parameter model can fit on that, in terms of, but I don't know how much this asphalt, and I haven't seen anybody who works with the size, equivalent size of the fracture process zone. But all materials has a process zone. That's a process zone that happens ahead of the crack front. And I really don't know how this could be measured in asphalt, for example. In terms of, because you have the fracture energy, but I still think that I don't know if in terms of the fracture energy, how this is well established, that the fracture energy that you calculate for a DCT test for asphalt, this will be really a material property, even the initial one, because you have the initial and the total one. The total one depends in all the tail of when you test like, let me show here the graph for the test that you can imagine that this is asphalt. For example, you have the CMOD, that's the same thing that's happening in asphalt. So if you have the load and the CMOD, so all the fracture energy will be this area here. The initial one will be an initial that's just responsible for this peak here. So I don't know how well tested and established asphalt is to say that this fracture energy is a size and shape independent, because even in concrete you have some size and shape independence. And asphalt you still have the rate independence because the viscoelasticity of the material there. So we have more unknowns to see that this is a really material property. But for example, to extend this model to asphalt, first you have to have fracture properties that you can say this is a material fracture property that is independent of the way that you do the test. And I don't think that in asphalt they already arrive in something like that yet. One of the best trials that was done here with Professor Butler and co-authors in the GCT, but I don't know how they are still using it. I think that they are, right? But not in terms of fracture properties that you can say, oh, this is independent. I don't know if just in a comparative way. I really don't know how is the state of the art in the GCTs. You guys can tell me better how this is being used in terms of fracture energy.
What do these hysteretic loops represent in that plot?
Yeah, it's just the load and unloading because you just calculate the fracture parameters here with these different compliances. Because the compliances is the inclination of this load and the unload.
But they represent the propagation of the crack.
Yeah, the propagation of the crack. Because you load, you are...
This is not a monotonic test? This is like a repeated?
No, this is a cycle one for the properties, because this is the lab scale. To calculate the properties, a cycle. But it's not an entirely cycle. You did this to the curve be like a kind of nice. You just need like at 1 or 2 cycles this because you just need the compliance of loading and the compliance in unloading here to calculate the parameters there. You have this in the pavement design too, right? This,
yeah, next semester.
you calculated there?
All right, let's thank Junior one more time for his
Thank you for your attention.